discovered these identities. Today we're going to take some time and look at another way in which we can use these identities to solve problems. Remember that the goal in this chapter is going to be solving more complicated trigonometric equations than what we were able to solve in the previous chapter. So that's the end goal. Before we can get there, though, we need to talk about how we can manipulate combinations of these sine, cosine, tangent, etc. That's what we're going to be working on here with the identities both today and then next time. Everybody's cool? Okay. So this type of problem we're going to do 3 examples for, and then as a class we're going to do some of the homework assignment. So this type of problem is called simplify the expression. So when you're asked to simplify an expression of trigonometric functions, you really have 2 tools at your disposal. You have algebra stuff, so things that you could do algebraically like factoring or foiling or combining like terms or making a common denominator or reducing a fraction, stuff like that. And then you have identities that you can use. So can I transform one of these trig functions in such a way that makes this simpler? So when we talk about simpler, what you're talking about is the fewest number of terms and the fewest factors in each term. Ideally, you can get it down to just one thing. At that point, you know you're done. So if I look at our first example here, it says sine cubed x plus sine x times cosine squared x. That's 2 terms because we have 2 things that are being added together, right? The second term contains 2 factors, right? I have a sine x times a cosine squared x. Is everybody okay with like the vocabulary of terms versus factors? Terms are things that are added or subtracted. Factors are things that are multiplied or divided, right? Okay. So when we say simplify the expression, what we're going to hope happens is at the end, we're going to be left with just one single trig function, right? Just one thing. So my tools to get there, again, algebra, or an identity. Typically, the first thing that I look for when doing one of these problems is I look for something algebraic to do. So let's look at this first example. Sine cubed x plus sine x times cosine squared x. And let's look to see if there's anything algebraic that we can do here. Again, when I say algebraic, I mean like factoring, foiling, combining like terms, common denominator, reducing a fraction, stuff like that. Now, 2 of these right away are out, right? What 2 algebraic possibilities are gone immediately just from looking at this? Well, the things involving fractions, right? Do I have any fractions here? No. So do you think common denominator is going to be something I could do? Well, no. How about reducing a fraction? Well, no, there's no fractions in this problem, Mr. Gulick. Okay. So we're down to like combining like terms, foiling, and factoring, right? Are there any parentheses here? Will there be any foiling to do if there's no parentheses? No, that's out. So we're down to combining like terms or factoring, right? Are there any like terms to combine here? Miriam, you're shaking your head no. Why not? Because I see a sine and a sine.
But they don't have, but one is like to the third.
Great. And the other one has also got a cosine multiplied to it, so I can't add before I've multiplied, right? So 2 great reasons there. So is there any like terms to combine? So we're left with one thing left as a possibility, that's factoring, right? As of this point, you've probably talked about two types of factoring in your algebra classes. So one goes all the way back to like pre-algebra. That's like a greatest common factor. You know, like you say 2x plus 4 equals 2 times the quantity x plus 2. Right, where I just factor a 2 off. And then there's quadratic factoring, right? Like x squared plus 5x plus 6 equals x plus 2 times x plus 3. Which one of these does this look quadratic to you? You better say no, because you don't even see anything squared in here, right? Couldn't possibly be quadratic. So the only algebraic possibility that we have is if there's a greatest common factor. Take a look at this for a moment and see if you see a greatest common factor. There is one. Who sees it? Jacob. It's not x because there's not actually any x's in this. What you have is a sine x, a sine cubed x, and a cosine squared x. Those are all one thing, right? Because sine is not a number, so sine x isn't sine times x. It's like one thing. Those things are stuck together. You're not going to be able to separate them ever. Do you want to take another shot at it? Okay, fair enough. There is a greatest common factor. It's not x, we've established that, right? But what is in common between sine cubed x and then sine x times cosine squared x?
Sine x.
Sine x. Is everybody okay with that? So if we factor sine x off to the front, what does sine cubed x become after we factored off a sine x? Sine squared x. Very good. Is everybody okay with that? What does sine x times cosine squared x become when I factor sine off of that? Very good. Cosine squared x. Notice that if I distribute the sign back through, I have exactly what I started with, right? That's our check. You should be able to see that without having to write anything down, just by using your eyeballs. Everybody's okay? All right. At this point, there's no more algebraic thing to do other than, well, I can multiply the sine x back through and go back to what I started with. Let's not do that, though. So if I've exhausted the algebraic things to do, I should now look for an identity. So take your identity sheet that I just passed out to you. Look at the side with the identities, not the unit circle. And just take a look through and see if you see anything that looks like it would be helpful to use in this situation. Who sees something that they think would be useful?
P1.
Hannah says P1. Why did you say that, Hannah?
It's sine squared plus cosine squared.
Great, and that's what we have right here. So what does P1 say sine squared plus cosine squared is equal to?
1.
So I can replace all of that in blue with just 1. In general, when I see I have something squared that's being added to something, like we do here, we have sine squared plus cosine squared, I'm going to take a look at my Pythagoreans to start. If I have something squared and then addition or subtraction going on, I'm going to take a look at my Pythagoreans because oftentimes those will be quite useful. What is sine x times 1? Sine x. Not a trick question. And that's just a single thing. So we're all done. What do you guys think? So here's the catch with these problems, right? Is that there's not just like one set procedure for doing this. There's lots of different ways you could do these. Some of them are going to be faster than others. As long as what you're doing is legal algebra and a legal substitution using a real identity, you can eventually stumble your way into the correct result. If your algebra is bad, you'll never get the right answer. Or if you misapply an identity, you'll not get the correct answer. And none of these problems are really the same. Each time it's going to be like its own separate little puzzle. So what we're going to try to do over the course of the next couple of days is try to develop some intuition. We're going to see a bunch of different kinds of tricks that we can use so that you can see these things and maybe recognize where they could be used into the future. We're going to talk about what could you do and why it would be a good or not good decision, or why, if it would be okay to do, but maybe just not the best thing to do, what might be better, what might be worse, just to try to create a little bit of intuition so you guys can see these problems and kind of see what to do. Because it's no two are really alike. It's not just like you can watch me do the procedure 3 times. I'm just like, just keep doing this procedure. It's not a problem like that. Let's look at the next one. So here we have secant x minus 1 times secant x plus 1 all over sine squared x. What do we typically start by looking for? Something algebra to do. Does anyone see an algebraic thing we could do here that looks like a good idea? Take a risk and volunteer. We got to get used to doing this. It's the only way we're going to get better. Iden.
Divide by sine x.
What do you mean by divide by sine x?
Are we still on 2?
We're looking at number 3. We finished 2 because we got down to a single thing. We're doing 3 right now.
FOIL.
Yeah. If you look at the numerator, that looks like a FOIL problem to me, right? I have 2 parentheses sitting next to each other. Everything I know from Algebra 2 says maybe try foiling that out. Now, ideally, that's a problem you could FOIL out in your head. And you say, Mr. Kulik, how am I supposed to do that in my head? Well, hopefully, once I point this out to you, you recognize that that is a difference of 2 squares. Remember that factoring pattern from last year when you factored quadratics? So I'm just using it to go that direction. But I know that a squared minus b squared is equal to a minus b times a plus b. So if I have a minus b times a plus b, that has to equal a squared minus b squared. So I'm just using that factoring pattern to go in the other direction. Now, if I FOILed that out, would that be okay? Yeah, of course it would. Are you going to get the same answer? Yeah, eventually. Are you going to have to like write out a bunch more stuff and like combine some like terms and blah, blah, like, yeah. I'm just trying to show you the shortcut. Because we use that, that'll come up a lot. Like the difference of 2 squares multiplication pattern will happen a lot. So just good to see it. And to remind you of that shortcut existing. Everybody's okay? Okay. So now we're at secant squared x minus 1 over sine squared x. Does anyone see any other algebra stuff to do? I don't either. I see Kate shaking her head. So what should we look for then? Identities, right? So take a look at your identity sheet. Go through and see if you find a relevant identity. Who wants to take a shot? Take a risk, somebody. Might as well do it now, because when we, in like 5 more minutes, when we start doing the homework as a class, you're not going to have a choice whether you want to take a risk or not. I'm going to make you take the risk. It's okay to be wrong. That's how we learn, right? Okay. Q1, you would need tan theta, and Q2, you would need cotangent theta. I don't see either one of those in my problem, so I probably wouldn't be looking at the Q's. See how nice I was about that? And I just gave you a nice reason for why I don't think I would be looking there, or why that's probably not the place to be looking. Let me give you a hint. When I see something squared, and then either addition or subtraction next to it, where do I look? I look at the Pythagoreans, the P's. So try looking there. Which P seems like the relevant one? Okay, so I could use P1 to rewrite sine squared as 1 minus cosine squared. I would not do that, though, because I would rather not go from from one term to 2 terms. I would use P3. What does P3 say? It says secant squared is equal to tangent squared plus 1. So I'm going to replace my secant squared with tangent squared plus 1. But Mr. Kulik, you just said it's a bad idea to turn one term into 2 terms. That's true, I did say that. But look at what I can do now. What can I do in that numerator now? The 1 and the minus 1, what are they going to do? Just add to give us 0, right? You see that we've now eliminated a term from the numerator. You guys see that?
Where did the secant go?
So I replaced secant squared with tan squared plus 1. Look at P3, and look at what P3 says it equals.
Oh.
Right? So that's what I did. You see it now? And it's, again, like, ask if you don't understand what I did. This is a little bit different than things we've done in the past. It's not the same pattern, the same procedure over and over again. You have to just kind of get used to, you have like 2 sets of tools. Figure out which tool you need from which toolbox. Okay. So now I have tan squared over sine squared. Is there anything algebraically I can do with this? Is there anything to FOIL? Well, no. Is there anything to factor? No, just like one fraction. Is there anything to combine like terms with? No. Can I reduce this fraction? No, because they're different trig functions. Can I make a common denominator? Well, there's only one fraction, Mr. Cooley. You can't do that. Okay. So nothing algebraic to do. You guys agree? Okay, let's look for an identity. Here, what I'm going to be looking for, because I have no addition or subtraction, and the stuff inside my trig function is both x, I'm going to really be limited to looking at the reciprocal and quotient identities. Specifically, I want to look to see if there's a way to rewrite tangent so that it would have a sine in it, or rewrite sine so that it would have a tangent in it. Because I'm hoping that somehow when I do that, the other one will cancel out. So look at your identities, specifically your reciprocal and quotient identities, and see if there's something in there that'll let me rewrite tangent so that it has sines in it, or rewrite sine so it has a tangent in it. Great. So Kate says Q1. Now Q1 has two different versions. Do you want to rewrite the tangent as sine over cosine or as secant over cosecant? Great. I agree, because we already have another sine in the problem, right? Now let's hold on 1 second, because our identity sheet says tangent equals sine over cosine. We have tangent squared, which is not the same thing. Can I still use the quotient identity here? Well, you told me to look here, Mr. Kulik, so you better be saying yes. The answer is yes. But tangent squared, okay, let's say if tangent equals sine over cosine, tangent squared is going to be sine squared over cosine squared, right? Everybody's okay with that? So we used Q1 here. So that's the Q1 that I used. I highlighted in green what I did. And now you're thinking, Mr. Kulik, but you took like a thing that wasn't a fraction and you made it into a fraction. It doesn't seem like it's getting simpler. Not at the moment. But what can we do? What does writing it this way allow me to do? Or us to do? We're doing this together. Okay, so what I would think about, you're on the right track. So I would think about the denominator, sine squared, as a fraction sine squared over 1. And now if I look at the compound fraction, the fraction on top of fraction, I can reduce. What do you notice about the numerator on the top and the numerator on the bottom? They are the same. What is that going to allow me to do? Reduce. Yeah. Now, when I reduce a fraction like that, when I cross them out, what do they become? Let me pick a different color here. What's that, Jacob? 1 is correct. Is everybody okay with how I wrote it this way? But goodness gracious, Mr. Kulik, I don't need a compound fraction anymore, do I? What can I just write this as? 1 over cosine squared x. Right? This is just 1, and anything divided by 1 is just itself. So 1 over cosine squared, right? Okay. Any algebraic thing to do here? I agree, no algebra, says Lexi. So what do we look for? An identity. Now we're in the same boat really as we were when we had tangent squared over sine squared. I'm still going to be looking at the reciprocal and quotients. Do we see a good one to use here? R5, yeah. R5 says 1 over cosine theta is equal to secant theta. Since we have squared, 1 over cosine squared is going to equal secant squared. That's one thing now, not a fraction. Better than a fraction. So we'll call that finished. So that was our identity R4 right there, or R5, excuse me. Is this starting to feel a little bit more familiar? We're getting a little bit intuition, seeing the things that are similar, although there's no like fixed pattern, but it's just me looking for algebraic thing, no identity, okay, do some identity, look for another algebraic thing to do, okay, do that, you know, no more algebra, look for an identity and keep going like kind of in that fashion. Let's do the last example here that I have picked out. How do we start? We look for algebra thing to do, right? Do we see anything algebraic to do here? Jake, what were you going to say?
Something with like cross subtract or something cross.
That's not a thing. Cross subtract.
Something with the cross. Like the cross multiply.
That's a solving technique, not for simplification. Can I do that? Think careful. The answer is no. Hold on a sec. I'll be happy to come back and get whatever you're going to say. I just want to finish this thought. That's okay. That's okay. So we can't do this, although, Mr. Kulik, I do this sometimes, right? When is it okay to do this? So if I had this problem where it's multiplication in between, then yes, we can cross out the cosines. What do we have in between our cosines here? Subtraction. Cannot reduce across addition or subtraction. Multiplication, go for it. All right. Miriam, what were you trying to say now?
Multiply both sides by
So there's not two sides because there's not an equal sign.
well, that's what I meant. Both fractions.
So you mean making a common denominator is kind of what you're saying. So between the denominator 1 minus sine x and the denominator cosine x, what would the common denominator be? So one denominator is 1 minus sine x, and the other denominator is cosine x. And we need to make a common denominator because we're being asked to subtract two fractions. What would that common denominator be? When you say put them together, can you elaborate what you mean there? If you meant times instead of plus, that sounds good. So what Jacob is saying is 1 minus sine x and cosine x are relatively prime. They have no factors in common with each other. Like if you're trying to add 1/2 and 1/3, the 2 and the 3 have no factors in common. So to find the common denominator, just multiply the two denominators together. If I'm adding 1/2 and 1/3, the common denominator is 2 times 3, 6. So here, I will multiply the top and bottom by cosine x to the first fraction and 1 minus sine x to the second fraction. Because the 1 minus sine x and then the cosine x. So you're basically taking what is the first fraction missing from the second fraction? Well, it's missing a cosine x. And what's the second fraction missing from the first fraction? 1 minus sine x. So if I multiply the numerator out, cosine times cosine is cosine squared x, good. And then here we're going to have to distribute the sine x through. And don't forget there's a negative sign there. So negative sine x times 1 is negative sine x. And then negative sine x times negative sine x is positive sine squared x. And then I never multiply my denominators out until I'm sure I have to. Because more often than not, what I'm going to want to do is reduce. In order to reduce the fraction, the denominator has to be in a factored form. So I never multiply denominator out unless I know I'm going to get something good out of it. And if I don't know it right away, I'm just going to leave it until I see that, oh yeah, I guess I do need to do that. But I never start with it. Okay. Let's look at the numerator. Any algebraic thing left to do up there? Kate, you're shaking your head no. I agree. Again, there's nothing to reduce because the numerator isn't factored yet, so I can't do any reducing. There's no like terms in the numerator. There's no greatest common factor between cosine squared x, sine x, and sine squared x. So there's nothing to factor there. Obviously, there's no foiling to do. So what do? I look at my identities. Look at your identity sheet. See if you see something good to do. Yeah. So, but Miriam, when I look at P1, it says sine squared plus cosine squared. I have like this 1 minus sine in between. Isn't that a problem? You can't, no factoring to do. But why isn't it a problem? Because you're just adding, right? Can you add things in any order you want? Can I just write that as sine squared plus cosine squared minus sine? Can you just do that? Of course you can. So that's going to give me my P1. So again, sine squared plus cosine squared is just 1. What can I do now? I can reduce the fraction by crossing out the 1 minus sine x's that are now common. Remember, when I cross them out, though, what do I get? 1s. So on the numerator, I have a 1. In the denominator, I have cosine x times 1. Well, I'm just going to write that as cosine x. This is looking pretty good. Is there any algebraic thing to do here? Of course not, Mr. Kulik. It's just 1 over a thing. Well, what should we do? Look at our identities. Where should I be looking at my identity sheet? Yeah, the R's and Q's, specifically R5 is the one that we need, which says that secant theta is 1 over cosine theta. It's exactly what we have. And we're done. All righty. So today in class, we are going to be doing 7 through 14, as much of it as we can. Anything we don't finish would be considered homework. We're going to do this as a group. So the group, or do this as a class, I'm going to call in these groups one at a time to ask for something to do. You're going to give me something to do that you think is a good idea. We'll talk about it. I might ask you to try something else if it's not such a good idea. After I tell you why it's not such a good idea, while the other group is doing it, you should be thinking the exact, or should be trying to answer the same questions I'm asking them to practice building up your own intuition on how to do these problems. Does everybody kind of get what we're going to do? We'll just go straight through in a line. You know, group 1, I'll ask a question to group 2, the group 3, and then we'll just cycle back through and we'll keep working through problems as far as we can get today. Now, while we're doing this, should you write this down? Well, yeah, it's your homework assignment, right? We're going to do maybe all of it today if we have enough time. Depends on how fast you guys are at answering me. It hasn't been very fast so far, so I don't think we'll finish, but that's okay.
Are you writing this down too?
Yes, of course I will.
Okay, so it's already going to be posted?
Yes, of course it will.
I really need to write it
I mean, you have to turn it in at some point in your own writing.
down. Like on my computer?
Yeah.
Okay, so I'll just copy it down tonight.
Okay. All right. So group 1 is, oh yeah, why don't you guys like stand up and move by your partner so you can talk to this person when I ask you to do stuff. Stand up, move. Or partners with absences. I have one group of 3, everybody that was lost a partner. I just put together in one spot. Just so you know, these groups were randomly generated. So I wrote this computer program to randomly generate groups or call on random students or do a bunch of other things. So this is the code that I wrote to do that. So it's not me making the groups. The computer randomly chose them.
Is it chapter 5 problem?
Yes. Yes. Group 1 is Kate and Lexi. We're going to be doing 7 through 14. On number 7, what should we do first, algebra or identity? Okay, what algebraic thing could we do here?
On number 7.
On number 7. No, you cannot. But I'm glad that you wanted to check first before diving into an identity. So there is no algebraic thing to do. What identity could you use? Okay, Q2 to turn cotangent into what?
Cosine over sine.
Great. Why did you pick that version?
It has the sign in it.
Yes, very good. Is everybody okay with what we did there? Let's see. Wade, Andrew, and Iden. What can we do? What should we do next? Algebra or identity?
Algebra.
Okay, great. What algebraic thing would we want to do here? Okay. So I would say, let's think about sine u as sine u over 1. And since that's multiplication there, what can we do? Well, not cross multiply, that's a solving technique. But what we can do is just reduce. When we reduce, those become ones. And what do I get when I multiply that all out? Just cosine u. Is there anything more to do? Nuh-uh. You're done. Look, you guys did this all by yourselves. That wasn't so bad. Charlie and MJ, looking at number 8. What would you like to do first? Algebra or identity? Okay. What algebraic thing would you do? So that you can do things like factoring and foiling and combining like terms and reducing what?
Two of the same ones, I guess, maybe. Divided by.
You want to reduce the fraction?
Yeah.
Yes.
But x.
Not by x, by a cosecant x.
Oh,
So I have one cosecant x on top, and I have two factors of them on the bottom. So I can reduce like that, right? Like if I have x over x squared, that just becomes 1 over x. That's good. Okay. Thank you, fellas. Who's next on my list here? Dom and Jake. What are we thinking next?
Algebra.
Okay, what algebra do you think you can do here? There isn't any algebra to do here. So it's an identity time. Yep, for sure.
Q2.
Okay, so let me say something first. Right now, we have, in order to reduce or combine like terms or to cancel anything, the inside of your trig functions need to be the same. Right now, I have tangent of pi over 2 minus x, and then cosecant of x. As they're currently written, the insides are not the same. So any identity I use, I'm not going to be able to cancel anything because the insides are different. The first thing I would be trying to do after I've done that reducing is to see if I can make the insides the same. So when I see a pi over 2 minus x, I'm going to be thinking, I'm going to start looking at the co-function identities because that's going to allow me to replace that with just an x. So if you look at the co-function identities, do you see a good one that we could use here?
C3.
I think you probably mean C6 because we have tangent of pi over 2 minus x that allow us to turn that into cotangent x. Okay. Thank you, fellas. Hannah and Jacob. What are we thinking next? I agree. Identity time, it seems like the time to me, we have a single fraction that doesn't reduce. Good. So you're going to replace cotangent with which identity? Cosine over sine or cosecant over secant? I agree. Why'd you pick that one? Because we already have a cosecant in there. Absolutely. Miriam and Maya. What can we do next?
Do the cosecant cancel out?
Yes. And what are we left with then?
Secant.
Close. 1 over secant. Thank you, Maya. Remember, when they cross out, they become 1s. And you can ditch the 1s in the denominator, but you can't get rid of a 1 in the numerator. Those need to stay. And then our last set of peeps is Francesca and Jack. Oops, get back to there. What are you guys thinking next? R2, great. And that'll allow us to rewrite that as cosine x, which will finish the problem up. So far, so good? Okay. Can I point out to you that maybe sometimes the easier way of thinking about this, when I'm about to use a quotient identity, is oftentimes I'm going to think about, instead of cotangent over cosecant, think about cotangent over 1 times cosecant over 1. So when I use Q1, yikes. I can think about it this way. And that's a little bit cleaner for me. We end up at the same spot. We're doing the same thing. Sometimes that work is a little easier to follow and not get lost, not lose a numerator, not lose a 1 over or something if we do it that way. But it's the same work, accomplishing the same thing. Okay? So that's the way I typically think about them when I'm doing it. I just thought I would share that. All right, 9, back to the top of the order. That is Kate and Lexi. What are you thinking here on number 9? The person that goes first has always got the hardest job, because you're seeing it for the first time. Everybody else has been looking at this and been thinking ahead. Yeah, there's nothing algebraic to do. That's very good.
Is it Q2?
You can't use Q2 because you don't have cosine over sine. You have 1 minus cosine squared over sine. So if you had like a cosine times stuff in the numerator, you could do a Q2. But since it's like cosine added or subtracted from stuff in the numerator, you cannot use Q2 there. Definitely a P. Probably not 2, because I don't see cotangent or sort of cosecants anywhere in my problem. P1. Now, how am I using P1 here? I'm going to replace the 1 with sine squared plus cosine squared. And you're like, Mr. Kulik, that seems like a tremendously bad idea, because like all you're doing now is making like that numerator so much worse. Now there's 3 things in there. Wade, Andrew, Iden. Seems like we made the numerator worse. Is that really true?
Combine like terms.
Yeah, we can just combine like terms. Specifically, what like terms are you looking at?
Cosine.
Yeah, the cosine. We have a positive cosine squared and a negative cosine squared. Those just combine to give us 0. That leaves us with sine squared over sine. What can you do with that?
Square.
Well, not square root it. If I'd like x squared over x,
Add it, that makes sense.
not,
X.
what if I had 4 over 2? So you reduce the fraction, right? So how does that reduce? And you're just left with sine x. Yep. Is everybody okay there? Guess I should do that. All right. I think 10 is possibly the trickiest one. Charlie and MJ, you guys are starting us off. See if you... So I would say this can be very easy if you make the right choices, and it can be pretty lengthy if you kind of go about it a different way. What are you thinking to do first? Algebra or identity here, fellas? I would not do an identity here first. I think this is an... What? What? Hold on. What did you say?
Would you add the tangents first?
We can't add the tangents because you don't have a common denominator. So what might you want to try then if you don't have a common denominator? Make a common denominator. Now that's a good idea, but there's a better idea yet out there.
Oh, could you like split them somehow?
You can't flip them. You can't make reciprocals without a reason to do, like something telling you that you need to do it. Now, if it was a solving problem, that's a different story, but it's not. Now, you notice something about the tangents, right? The numerator is the same in each of them. So what we can do is we can factor. What is the greatest common factor here between the two fractions?
Tangent x.
The tangent x. That's correct. So when we factor that tangent x off, what does the first fraction become? Close. It is 1 over cosecant squared. And so what does the second fraction become?
1 over secant squared.
Excellent. That's our best first step. I want to be clear. Making a common denominator is a good idea. This is a faster way of doing it, and it will require no common denominator at any point along the way, which is the cool part about the way I'm going to show you to do this one. Let's see, who's next? Dom and Jake. Algebra identity. What do you think you want to do?
Do they have similar
I have 1 over cosecant squared plus 1 over secant squared.
we do the algebra because they're both square with the square?
What are you thinking you're going to do? Okay, I like that idea better. What identity do you want to do? Or identities?
R5,
Okay, and what other one?
R4.
Well, not R4 or R5. You're thinking R1 and R2.
Yeah.
So R1 is going to change 1 over cosecant squared into what?
Sine
Squared.
squared.
Yup. And R2 is going to turn 1 over secant squared into?
Cos squared.
Yes. Very good. All right, who's my next group? Jacob and Hannah. What do you guys? Oh, Hannah, it's on you. Jacob's in the bathroom.
Q1.
You could use Q1 to change tangent. I would not, though, because there's a better identity to use here. You could. It's not helping us get any closer to the finish.
Is it P1?
Yes. P1 will allow us to say sine squared plus cosine squared is 1. And then 1 times tangent is just tangent. And we're done. Notice that at no point did I need to make a common denominator. Didn't have to try to add fractions or reduce fractions. It's a very sneaky way of attacking that problem, but boy, does it make it easy once you've seen that as a trick. Miriam.
Oh, what does it say right after the 10 and then X?
It's just a bracket with a 1 in it,
Oh, okay.
because this stuff is 1. That's what P1 says. I think that's the trickiest one of the lot. It's the longest one if you don't take this route. And this route is kind of tough to see, right? You really have to have done a bunch of these to be able to see that the first time. All right. Where are we at next? Hannah just went. So we're Maya and Miriam. You guys are starting number 11.
I feel like there's no algebra.
Great. I agree with you.
So P1 maybe?
Yeah, absolutely. Because you see the sine squared plus a cosine squared. That's great. Okay. After you guys is Francesca and Jack. What do you guys see to do there? Awesome. Yes, absolutely. We see right away that 1 plus 1 plus tangent squared is secant squared. And then, are we back to the top? Yup. Kate and Lexi. Reduce. Yeah, that's what you're trying. That's the word you're looking for, is reduce. So we're left with just secant beta, and we're done. All right. Who's next? Okay. Wade Andrew Iden, looking at number 12. What are you guys thinking? Nope, we can't cancel x's because the x's aren't like a thing. We have secant negative x and cosine negative x, but there's no actual just like x, right? Those are like locked inside those trig functions. So you have to think about that as like one object, like a secant negative x. So it might be tempting to think to use one of the odd-even identities to change those negative x's to positive x's, but you don't need to do that. You can, it's not wrong to do it. That'd be the correct use of that identity. But because the insides are both negative x's, you don't need to do it. As long as the insides are the same, there's no need to change them back to just regular x's.
R5.
Yeah, I think that's a great idea. If we just use R5, we have this. So what can I do with this? And I'm left with it's the easiest one on the sheet. Now you could use the odd-even identities to make that negative cosine or cosine of negative x into cosine x and secant of negative x into secant x and then do the same thing. Perfectly fine to do that, still correct, but you don't need to.
Could you do R2 as well?
Of course, yeah. Yeah, you could have turned this cosine into 1 over secant and canceled the same way, for sure. Absolutely, good question. All right, 13, who's up next? Charlie and MJ.
Well, no.
So I think you're going for identity.
Yeah.
That's correct. You should be doing that.
I think-
Yes. Yeah, so Charlie says C1. We're going to change this guy into sine alpha. And that's we need to do that at some point. Now is as good a time as any, because what it's going to do is it's going to allow us to get the insides of all of my trig functions to be exactly the same, right? Now we just have alphas across the board. Didn't have to be done first. There's other things you could have done first, but it needs to be done eventually. Might as well do it right now if that's what we see. Good. Next up would be Jake and Dom. What are you guys thinking?
Identity.
Great. Which identity do you want to use? I'll give you a hint. You should be looking at, no, definitely no C's. You should be looking at that package to do something with. Well, you don't have anything squared, right? So you can't be using any of the Pythagoreans. Should be looking at R's and Q's. Well, I wouldn't do that because turning tangent to 1 over cotangent is fine. You can do that, but you don't have any other cotangents anywhere. I would try to see if there's a way to turn tangent into something with a cosine in it, or cosine into something with a tangent in it. Q1 is a much better idea, yes. So that's going to allow you to turn tangent into sine over cosine, right?
Yeah.
And why is that an improvement? What does that allow us to do by changing that? Yeah, we can reduce out the cosines. And what can I do now? Yeah, add the sines to get just one sine theta or sine alpha, right? Cool. All right, who comes next? Maya and Miriam, you guys are going to start 14 for us.
Wait, I have a question.
Yes, go ahead.
Is it like, is that like a negative sine theta? Like,
You can think about it, sine theta minus sine theta plus a sine theta. So it's like,
okay.
so you just have one left, right? It's like
Yeah.
2 minus 2 plus 2.
Okay.
Well, the 2 minus 2 is 0, and then Maya says what? You cannot reduce because there's no factor in common in either the numerator, denominator, or the fraction. You can't do this because you have the minus, because it's addition or subtraction. Has to be multiplication in order to reduce.
Would it be like R4 or something?
Can't use R4 because you don't have 1 over sine. You have 1 over 1 minus sine and 1 over 1 plus sine. You need to be doing an algebra thing here.
Oh.
What algebra thing should we be doing if we have two fractions that we're adding together? Common denominator. All right. What would the common denominator be between these two? Is there any factor in common between 1 minus sine y and 1 plus sine y? Sine is not a factor because it's not being I don't have 1 times sine. Factor means multiply. Is there any common factor in between these? No, right? One, or sure, 1, yes, the 1 is always a common factor, but like no. So what would we need to multiply, or what would the common denominator be? It's just the product of the two. 1 plus sine y times 1 minus sine y.
Good afternoon, Notre Dame. Let us end this day in prayer. We ask your blessing, Lord, on those who show real concern for the spiritual and material good of their neighbors. Lord, hear us. Lord,
Wait for me to finish
increase
this
our
one, guys.
faith as
We can
wait
do it
in
real
hope
quick.
For the coming of our Savior. Lord, hear us. Students, teachers, have a great rest of your day and stay safe. In the name of the Father, and the Son, and of the Holy Spirit. Amen.
30 seconds for
Teachers,
me
you
to
may
finish.
dismiss that you're ready.
30 seconds is all I need. So I'm left here, 2 over 1 minus sine y times 1 plus sine y. Nothing to do, so I'm going to FOIL the denominator out. I'm going to use P1. These guys cancel out. I'm going to apply R5. And that's as good as we can do. Thank you. Have a good day.